Hello and welcome back to the Dragonfly Daily. We had a extended 4-day weekend with no lessons, but we're back today. My name is Mike Marsh. I am the product manager of Dragonfly at ORS. You can follow me at Dragonfly Wizard on Twitter, but please find me on ResearchGate or LinkedIn if you want, but definitely check out the YouTube channel for all of the Dragonfly Dailies. You can find that at orss.ca/YTP2. And while you're there, you can subscribe to the channel and get all of the other content that we are providing for Dragonfly users. Now, today's lesson number 37 lessons into this COVID crisis, and now we are on lesson 37. If you're watching on YouTube, hit that subscribe button now. Lesson 37 is on distance mapping, and I don't know why it says distance mapping down here. It should say Dragonfly 4.1. So through a peculiar set of circumstances, I am now separated from my workstation for a day, so I am not on my workstation that has the Dragonfly 2020.1 release candidate. We are using Dragonfly 4.1 for this lesson on distance mapping. That's Dragonfly 4.1. So I'm going to pop over to Dragonfly 4.1. We're going to look at some tools for encoding spatial distance, and we're going to look at Euclidean distance transforms, and we will look at geodesic distance transforms. You'll see what I mean. For data today, we're going to grab some data over from the Digital Rocks portal. On the Digital Rocks portal, there is this carbonate data sample that is from Tom Boltres and collaborators and colleagues. So folks like Maureen Boone and others have contributed to this carbonate data set. So you can go and grab this microCT data set, and you know how to import data into Dragonfly of type raw. You can just import it and type the width and the height and the depth and give it the data type. So we're going to do this data set, and then we're also going to look at the sand data set. That is a sand pack we've looked at before. If I search on this page for hydrate, I'll find it because it's labeled hydrate bearing sand. So the two data sets we're going to look at are that carbonate sample. Just realize you can't see the captions. We're going to look at that carbonate sample and this dry sand pack sample. All right. Oh, I thought they were already loaded. Let's grab these and... All right, now for the sand pack, I have a multi-roy that has labeled a bunch of grains. And I think actually during tomorrow's lesson, we'll combine distance transforms and watershed transforms, and we'll show you the process of separating these grains into individual labeled grains. Now, what we're going to do is we're going to look at computing distances from an ROI. And that can be useful for different scenarios. What you are going to see is that a distance transform by itself is almost never a solution or an answer. It's a tool for computing something else. But you're going to find out some useful ways of using it. So the first thing I'm going to do is I'm going to pick an individual grain from my multi-roy. I'm going to right click and I'm going to go to connected components and choose analysis. Now I have this open and I am in this state right here, the select objects, and so I'm going to select a grain. So this grain is now selected. You can see it's selected because it's brighter than all the other grains. And I'm going to export that to an ROI. Now, I have one grain encoded as an ROI. What I can do is I can take this grain, and I'll call this my grain of interest, and I can right-click on the grain. Actually, before I do that, I want to make a copy of it and discuss something. All right, so and I'm going to hide my grains multi-roy. All right, so I've got grain of interest, right? And we understand that there is a mathematical morphology operation called a dilate. And if I select this grain of interest and I come over to the segment and I choose morphological operations 3D sphere kernel size 3, which remember is a radius of 1, and I hit dilate, then all of these pixels that are not green that happen to be touching a green, they become green. So all of these pixels will become green when I dilate, then another layer of pixels, etc. So I'm going to hit dilate. And it grows, and it grows, and it grows, and it grows. A distance transform will work in a similar way, and it will compute the distance to the surface. And you can think of it as a series of dilations. And so all of the pixels that are captured in the first dilation are 1 pixel away, and all of the pixels captured in the second dilation are 2 pixels away. And so you can think of a distance transform as a mathematical morphology operation in the same family as dilate. Now, Dragonfly is sensitive to pixel sizes, and it knows that if the pixels are 5 microns in X and 5 microns in Y, but 10 microns in Z, it is capable of taking care of that when you do the distance map. So it will actually compute a distance in units rather than in pixels. Now I'm going to delete this one that I modified. I'm going to go back to this one. What you can do at any time is you can right-click on an ROI and you can say create mapping of a distance map. And it's going to create this Euclidean distance map. Now, this went very quickly. This is not the full SandPack data, which might be 1,300 slices. I just have 400 slices loaded up on my laptop here. Now, if we turn on the visibility of the distance map, what we see here is this image, and it's an image that has low intensity here and high intensity here. Basically, we have created a three-dimensional spatial encoding. Every pixel on this domain, which is this large three-dimensional volume, is now encoded with its distance to the surface of the grain. So it takes all of the green pixels, all of the pixels labeled in the ROI, and for every pixel in the image, it is going to take on the intensity that is the shortest distance from that pixel to any green pixel. Now the shapes can be quite complicated. I could select 5 grains, I could select the entire slice at the top. You can select whatever you want as the ROI and do a distance transform. So this distance transform is telling me in the image how far away is any pixel to the nearest green pixel. So I have this encoding. Now I'm going to hide it. Now what I'm going to do is I'm going to turn on my multi-ROI and I'm going to right click and I'm going to go back to analysis. All right, so I have the analysis panel open. I'm going to clear my selection. So I have all of these grains. And suppose I am interested in knowing for any individual grain, how far is it from my grain of interest? Well, we've seen that this panel here allows me to compute measurements. So I could say, what is the volume and what is the aspect ratio? We can also select our initial grayscale image data, which is called dry SandPack, and say, what's the mean intensity of every grain? And we can now, we have another image map. It is our distance map. And what we can do is we can say for every grain, and let's look at this a little more closely. Let's turn this on. And basically for every grain, I can say of all the pixels in this grain, what is the average intensity in the distance map, which is going to be the average distance from this grain to the grain of interest. Or I could say, what is the minimum intensity? So if I have some pixels in this grain that are only 100 microns away, and I have some pixels that are 110 microns away, then the minimum intensity is going to choose the one with the shortest distance. So if I choose minimum intensity, it's going to give me for every grain what is the shortest distance to the grain of interest. So I'll select minimum intensity, I'll also select mean intensity, and I'll hit OK. So it computes this for the entire table of grains. And now what we can do is, I'm going to go ahead and hide the distance map. So we can interrogate by volume, and we say, oh, okay, you know what, there's some false positives. These two grains are labeled as 1, so it looks like it's a bigger grain than it should be. I can color by aspect ratio. I can color by mean intensity. And it looks like most of these grains are probably all the same mineral, have the same intensity, but some grains may be a little bit lower intensity or a little bit higher intensity. Maybe they had some higher X-ray attenuation, etc. And we can scroll over to the distance map. Now if I click minimum intensity, what we have here is these grains that are very, very close, they have a very short distance. The grains that are a little bit farther, a little bit bigger distance, etc. So you can now map the intensity, or I should say map the distance of any single object in your objects analysis, the distance to a target. We could also do mean intensity. Now, the example I would show you if I had my workstation here is we could take the neuron cell we looked at last week and map every mitochondria and what is its distance to the plasma membrane, or what is its distance to the nuclear membrane. Or you could do the same thing for ER and say how close are all of my ER pixels, or how close is each ER segmented membrane from a mitochondrion. So you can do distance mapping to interrogate your different objects in object analysis. Now, that's what I wanted to show you with this mapping. Now, just the key here is you can do any sort of mapping, and if you had selected an entire plane of pixels at the top, basically every grain would now be encoded by how far is it from that plane. If you had selected a cylinder wall, then you would have encoded how far is every grain from the wall of the cylinder. So it doesn't have to be distance from an object like a grain or a nucleus. What's happened to my captions? Oh, they've started up again. Okay. So I don't have to do it from a single object. I could also have 3 different grains selected, and it would be the shortest distance to the nearest grain. So I think you get the idea. I'm going to go ahead and close this out. I'm going to remove my sand pack and remove my multi-roy and remove my grain of interest. And remove my distance map. Now, what I have loaded here is that carbonate sample I was mentioning before. If we look at this data set, we'll see that there's some carbonate, and then it's in some sort of sample holder or some sort of mesh. I don't know what's going on. But this is typical of a drilled plug that is imaged by micro-CT. Now, if I were to try and do some segmentation and I tried to threshold, then we might see something like this. The intensities in the middle of the image might be a little bit higher or darker. So intrinsically, there is a physics phenomenon associated with laboratory CT or any CT where you have a polychromatic light source, where this physics phenomenon called beam hardening will, without correction, cause the intensities on the outside to be a little bit brighter than the intensities on the inside. So that's one of the phenomena, or one of the symptoms that people mean when they say beam hardening. And so you can see that when I threshold, it's a little bit brighter on the outside. Sometimes you'll actually see the inverse, maybe a little brighter on the inside, but that's just because someone applied a correction routine and it overcompensated. Now, if we were to use a ruler tool and look at the intensity profile in this image, then you'll see that, okay, you see this is the intensity on the outside of the carbonate. Here's the intensity on the outside of the carbonate. And if you look here, you can see a little bit of a trend. So this is that beam hardening. It's also sometimes called cupping because you have a little cup in the middle of the sample. Now, why am I talking about this? Well, it turns out that for a cylindrical sample, that intensity profile as a result of the beam hardening very much corresponds with the radius of the sample. So it's only these pixels at high radius that have the true intensity, and it's the pixels at lower radius that have an intensity that's depressed by the beam hardening. I don't know if I should say true intensity, but that's the phenomenon. The pixels at high radius have very high intensity. Now I'm going to delete this ruler. Now the reason I mention all this is I can create a spatial encoding on my image that maps to radius. So if I wanted to, for any reason, understand where my pixels are or their radius from the center, I could use a distance transform for accomplishing that. Now what I'm going to do, I'm going to go back to the track state. I'm going to go back to segment, turn off my define range. And I'm going to create a cylinder, and I'll turn on the visibility of the cylinder, and I will reposition the cylinder by positioning these vertices so that I can get the cylinder roughly concentric with my sample. So I've got a cylinder here, and I can increase the radius and say that's not quite right, and I can, the sample, it's probably drilled out with a coring bit, but it may not be perfectly cylindrical depending on that. The behavior of that drill press or the behavior of the rock. I'm not an expert on sample prep, so I probably shouldn't speculate too much. Now that's pretty close to concentric. Now now that I've centered it appropriately, what I'm actually going to do is I'm going to pull in the radius really, really small. And you'll see why here in a minute. So I have this cylinder. I'm going to create an ROI, and I'm going to call this, I don't know, cylinder axis. And I'm going to right-click on cylinder, I'm going to add to ROI, and now I have these pixels labeled. So what I can do is I can right-click on cylinder axis, and I can say create mapping of a distance map. It's now going to create that Euclidean distance map, and every pixel in the image is going to have the intensity of what is its distance from that cylinder, or more precisely, what is the distance from the surface of that cylinder. And this is our radial encoding. So all of the pixels at low radius have low intensity, the pixels at high radius have high intensity. Now, one thing we could do is we could put together this radial encoding with the intensity encoding. And I don't know if you remember, but a couple of weeks ago we had a lesson on a tool called histographic segmentation. This allows you to interrogate 2 different images at the same time. So what you get to do in histographic segmentation is you get to choose an x-axis, and I'm going to choose the distance map we just made, and the y-axis I'm going to choose my CT scan intensities. I'm going to tell it 256 bins, and I'm going to tell it to compute the histogram. Now, if the data had no distance function, then it should have no difference in y. It should basically have the same intensity profile all across x, right? So you should go from 0 radius to high radius and it would be the same. Now what we see in this data set, so the first thing we see is, okay, once I get out here to about 150 microns, I see my intensity goes high to low. Well, that makes sense because I'm going from here to here. So all of these pixels out here are my low intensity pixels out here. But the other thing I notice is that the intensity of my low radius, everything between less than 150 microns, I think, everything at low radius is I've got some bright pixels for the carbonate, and I've got some dark pixels for the pore space, and it's pretty continuous here. It's not a very discrete, and that maybe happen because we may have microporosity or other phenomena going on. But the other thing you'll notice is in the carbonate phase, it takes a sharp tick up at the end. So we could segment in this domain, in the histogram domain, like we've seen before. So I could pick a region of interest, and then I could paint in the histogram domain, right? So I could paint at low radius and follow this sort of center line. And then when I get to high radius, I can just paint up here. And what we see now is we've segmented these pixels even though they are brighter than these pixels. So, and I can dilate in my histogram space if I want. So this is going to make all of these get a little bit bigger. So we don't have time to describe histographic segmentation all over again. You'll have to refer to that lesson. But you could do this to try and segment the carbonate phase, and then if you wanted to, you could try and you could export this and then segment the pore phase separately and do a watershed, or you could do the watershed directly from here. Now the watershed would take, I don't know, 20 minutes on a sample this size on my laptop, so I'm not going to do it for you now. But the idea here is we have created a spatial encoding based on the distance from the cylinder axis, which is effectively a radial encoding. So you can use distance transforms for doing a radial encoding. Now that's all I'm going to say about that. So I'm going to go ahead and close this out. You'll lose your ROI. Do you want to export your ROI? No, I don't want to export it. Okay, so I'm going to get rid of that. We're not going to use that again. Now, there are one or two more distance transforms I want to show you. So all we've done is the Euclidean distance map. And the next thing that we want to look at in the distance mapping discussion is looking at geodesic distance maps, which allow you to compute the distance from a source point into an ROI. And that may be a little difficult to explain by just using words, so I'm going to show you. Now I'm on my laptop and I'm not going to be able to work on this full data set, so we're going to work on a smaller version of the data set. What I will do is I will use the clip parameters so I can crop so that we can have a smaller data set. We can get something computed in real time that my laptop can handle. And let me look at the other axis, and we'll, oops, I was grabbing the color bar. All right, we'll work with something like that. I will right click and go to modify and transform crop and create a new data set. All right, now I have the cropped data set. What I'm going to do with this is I'm going to segment a little bit of the pore space just with a naive segmentation. So I'll come over here and I will create an ROI, and I will now just do a lower Otsu on the ROI. So define lower Otsu, that's fine, add, and now I'll call this my pore space. Now, what I can do is I can go to the top slice of the ROI, and I could paint all of the pixels on the top slice of the ROI, and I will call that my I don't know, my data source, my inlet, I don't know, whatever you want to think about it. I'll call it an inlet, and I think that'll make some sense for context here. What I'll do is I will go to 2D mode, and I will, oops, I need to create a new ROI, and we'll call this inlet. And now I will use the region tool, rectangle with define range turned on, and I can, now I have all of these pixels, well, almost all of them, painted blue. Actually, this might be more interesting if I don't paint all of them. Let's do a undo, and let's paint here. All right, now what I'm going to do is I'm going to take my pore space ROI, and I'm going to right click and say I want to generate a mapping, but this time I want to do a geodesic distance map. And it's going to ask me for a seed ROI, and I will choose inlet. Now I'm going to let that compute, and oh, it's already done computing. So what I have now is this new image, so I'm going to need to turn up the brightness on it. Oh, you know, maybe I chose a bad inlet. Let's have a look at this again. Oh, yeah, that's a terrible inlet. It has no connectivity to anything else. Let's try again. So let's delete this, and we'll edit the inlet, and we'll add some pixels. And I understand I haven't explained what this is doing, but after it's done, it'll be easier to explain. Let's just choose some of these pixels. And we'll repeat. Right-click on the pore space, go to Create Mapping, Geodesic Distance Map, use Inlet, and click OK. What it's going to do is you can think of this as, in some ways, like a simulated diffusion from the inlet. So now if we look at this image, then what we'll see is all of the pixels that are connected are non-black, or non-zero. The pixels that are a very, very short distance from the inlet will have low values, and the pixels that are higher distance will have higher intensity values. Now, if we look at this in 3D, so I can come over here in 3D, and I can say I want to use a 3D lookup table like rainbow. Let's find rainbow in here. And what I have is I have a mapping from the inlet, and we can see, oops, let's turn this off here. We can see the pixels, let's dismiss that. The pixels that are very, very, stupid zoom. The pixels that are very, very close intensity to the inlet have a low intensity, and the pixels that are farther distance from the inlet have a higher intensity. And so you see this red over here. What happened is it had to traverse this part of the pore space, and it got to these yellow pixels the same time it got to these yellow pixels, but here it was actually a farther distance from the inlet, a farther traversed distance. Yeah, that's a pretty good example. So you can see that this is different from the Euclidean distance. So these pixels are not based on their ruler or their Euclidean distance, they're based on their diffusion distance. And so that allows you to interrogate how far is something in a circuitous path. Now, the other tools I could show you, I wanted to show you today. Let me look at the time. Okay, I'll show you one more. The two other distance transforms work a little bit like this, but they actually work on the grayscale image. And if you right-click on grayscale image, you will see Dijkstra shortest path map and fast marching speed map. Now, I want to show you a little bit about what these do, but let's start in the image domain looking at the source image. You may remember in one of the early lessons we looked at some of the segmentation tools, and we said if you have an ROI, so you have to have an ROI selected for this, if you have an ROI, one of the tools in 2D mode is this. And what I can do is I can position my mouse somewhere in here, let's say right here, and then I hold down Control and I start dragging. And as I drag, it tries to fit a contour in 2D that tries to snap to the edges. Now, what happens here is as soon as you right-click, a 2D fast marching, this fast marching speed map is evaluated. And what happens is I look at all the pixels under the selected circle. So recall that when I was here, you can see a fixed pixel, a fixed circle. So it looks at all the pixels under that circle, computes the mean intensity, all right? Then it starts dilating out. And if it crosses from bright pixels to dark pixels, it will go more slowly. If it crosses from bright pixels to brighter pixels, it will go slowly. If it crosses from bright pixels to pixels of the same brightness, it will go very quickly. So this is a diffusion in the grayscale space, and basically it is penalized whenever it goes up or down the image intensity gradient. So this is a tool that allows you to evaluate the gradient, and later tomorrow we'll talk about the segmentation by watershed. And the watershed transform does something quite similar. In fact, it uses some of the same math. And it is looking for expansion in the grayscale space up until trying to converge on ridges. You'll see about that tomorrow. So suffice it to say now, with this tool, you can build a distance map that is how far am I in the tone of gray space. So it's a little bit difficult to compute, or I should say to interpret, since it will diffuse across the boundaries as well. It just diffuses more slowly across the boundaries. So if I just took let's take the inlet and we'll reset the inlet by doing clear, and I'll just paint a little 3D sphere right here. Okay, so all of the pixels of that sphere. Oh, wait, that was not 3D. Let's try again. Paint a sphere. So all of the pixels of that sphere are inside that pore space. So I could come right back to this image and say I want a fast marching speed map, and the seed I will use will be my inlet. Now remember, this is evaluating directly on the grayscale image, so it's going to evaluate on the tone of gray. So it's going to create a new image, and you'll see that all the low intensity values in the output image are those that do not have to cross a gradient. So if we look, let's turn this off and this on. So what you see here is it spread out from here, and it went everywhere it could, and the farther away it went, it has a higher value, and whenever it crosses a interface or a high gradient zone, it pays a higher value. So that tool we used in 2D, you could replicate on your own in 3D. It's not a very user-friendly interface for doing it, but you now could simply create a region and you could just interrogate here, right? Because if we define range and we do this, this is going to be everything that's very, very close to my seed, and this is going to be farther and farther. So it's going to be very much like that blow tool or that adaptive region growing tool, but now it's being done in 3D. So there's another tool in here called the Dijkstra shortest path map. It's similar to the fast marching speed map. You can actually use this mathematically to solve mazes. You can create a target and a source, and it will move through the image, and it'll actually the shortest intensity path will actually be the solution for solving the maze. But I don't really have time to get into it. All I want to say for today is we've looked at the Euclidean distance map, which operates directly on an ROI. The Euclidean distance map, which you right-click and do create mapping distance map. And one thing I did not mention is there's another variant of that, which is the signed distance map, which is to say you can compute all of the pixels that are distant from the ROI as positive values, and all of the ones that are distant towards the center of the ROI from the surface as negative values. We didn't look at that, but that's the difference between distance map and signed distance map. Signed distance map is not as efficient as it could be, so it'll be slower. Then we looked at geodesic distance map, which operates on an ROI. It will look at that, let's say, diffusion in the ROI space, but it will be considered from an inlet perspective. And then finally, we looked at the grayscale distance map. We looked specifically at fast marching, but there's also Dijkstra. So I'm going to stop there and move over to questions. Let's see what your questions say. All right. So there's a question. When installing 2020.1, a clean install it over 4.1 or install it along with 4.1? If it is the release candidate, then I would say install it along with 4.1. If it is the production release, then you have no reason, it should be stable enough for all of your work, so you have no reason to preserve 4.1, so you could install them both. You have no reason to preserve it, so you could overwrite. Now, if there's a difference and you don't like the difference, you could keep 4.1 around because you like the legacy interface for some reason, or if you want to have 4.1 for the legacy rendering engine, so it'll launch whenever you want, and you could launch 2020 for the new rendering engine, that's an option. But basically, I would say if it's the production release, then choose to overwrite. Okay, next question. Two simple questions. In the statistical properties tab, I could not see the median intensity. Can we have that? Yeah, so if you are over here, and I'll load up that so you can see where it is. Let's select all of this and remove, and let's do import. And I don't know if you're saying I don't have it or you don't have it. Like it's like I have it and you don't see it in yours, or it doesn't exist and you would like us to add it. Let's go to Connected Components Analysis, and if we come to measurements and we choose the intensity, all right, min, median, min, max, mean, variance. Okay, so median's not there. Yeah, we could add it. I'll have to have someone make a note to add it. There are also examples of how to add your own statistical properties. So it would probably be like a 1-hour exercise if you want to follow the documentation online and create your own median intensity property. All right. 2 simple questions. All right, that's the first question. Next question. The second is about the default cylinder orientation. Would it make sense to you to make the default is Z in the height direction? In my case, Z, always the CT rotation axis. Well, that's not true for all CT vendors, but keep in mind with 2020.1, when you have a cylinder, there are buttons at the bottom that let you say snap to Z, snap to X, or snap to Y for any selected data set. So if it's not the default, it's only 1 mouse click away for snapping, so you're good. Next question. When I try to dilate an ROI, nothing happens. I click dilate, and then nothing happens at all. I have the right ROI selected and define range turned off, so that's not the issue. You may have to send us the log files. What you should do if you're having that issue is go to help. Let's see. Go to in 4.1. It is going to be. I'm looking for the recorder. I guess suppose you go to Open Plugins and choose Recorder, and then hit Start Recording. Then select your ROI. Hit Dilate a few times. And then after you're done, hit stop recording, and you'll have a new video. And what I'll have you do is I'll have you report an issue and describe what you're seeing. Click send log files, and it says upload a file. Here you'll click this button, select the recording. Then we'll have the recording, and we can see everything you saw, and we can troubleshoot it for you. But it should work. I'm not sure what the issue is you're seeing, but we can fix it. Next, not a question. Hypothesis based on observations from the past months. Zoom loses the synchronization of sound when you are working with bigger data sets. The larger the data set, the worse the lag, and the faster it becomes noticeable. The lag doesn't seem to happen in the YouTube videos, so it is recording well, and I don't think it's being the workstation versus the laptop. Well, it could be that it has something to do with the data set. I don't know why the Zoom would rely so heavily on my CPU, or that loading up the large data and RAM would have that effect. That's interesting. The reason the recordings on YouTube are fine is because I'm recording them with a third-party recorder that is capturing my sound locally rather than in the cloud. But thanks for your notes. Next is, do you always use the regular distance map to run watershed on? Are there any cases where you would use other kinds of distance map for watershed for object separation purposes? That's a good question, Aya. Maybe there are some cases. I haven't thought about it. For splitting the objects or separating the objects, I've always used the Euclidean distance map. Maybe it makes sense to use a grayscale distance map. I'd have to think about it. It still is going to be critically dependent on what you use for seeds, and so I guess, since you can't have proper seeds in the grayscale distance map, I don't know. I have not thought about it. Now, Connor says Sobel, and Connor's comment makes a lot of sense. If your question is just about separating objects, then the Sobel might not apply. But the other very, very common application for using watershed is for segmenting. So if you want to segment, not splitting grains from each other, but splitting all of the grains from all of the pore space, then you could create a Sobel or an edge-enhanced filter function on the grayscale image, and then that would help you separate grains from background. And we'll look at that tomorrow. We'll look at the 2 major applications of watershed for segmenting the foreground phase from the background phase and for splitting the objects. All right. Last question. Is this fast marching the same one we can use for tortuosity estimation? Well, tortuosity means we all think we know what it means when we say it, but there are 10 different definitions in the literature of quantitative descriptions for tortuosity. So I don't think fast marching is giving you a tortuosity. It could enter into your tortuosity calculus. It would be worthwhile for visiting the tortuosity literature and seeing if there's any consensus now so that we could add a tortuosity computation. We do have tortuosity computed in the graph domain, but not in the ROI domain. And that means if you segment your pore space into a graph, we can tell how circuitous is the graph. So when you go from one node to another, is it a very indirect path, which we think is what you mean by tortuosity. Another question. What might be the reason when a trained network does not produce any segmentation when applied? It could be that the grayscale intensity of your training data is completely different from the grayscale data of your applied data set. So if you trained on images and the mean intensity was 50,000 and then you tried applying on data set where it's 10,000, then it would fail. If it's the same data set and you're not getting an answer, you can send us the parameters and we'll look into it for you. I mean, often the first or second epochs you may see 0 result, but then it converges to something useful within 10 epochs. So maybe just a little bit more training. If you've already trained for 10 to 50 epochs and you see nothing, then clearly there's something wrong and we could help you troubleshoot that. And we're very happy to get people to succeed with deep learning, so let us know what questions you have there. All right, that is the end of the discussion on distance transforms. Come back tomorrow, we'll talk about watershed transforms, and then on lesson 39, we will visit the topic of cylinder transforms, or at least that's the hope. Not necessarily cylinder transforms, but thinking about cylinder mapping or cylinder coordinate systems for interrogating data. Nothing very advanced, just some thoughts in that area. So thank you all for your attention. Thank you all for attending. Look forward to talking to you again tomorrow. Take care. Bye-bye.